Alright, this is for question number 47 in chapter 4. So after reading through the problem, the first part, it's going to ask you what's the speed at the instant this guy's feet touches the ground. So first off, we have to solve for time. So to do that, we have to use this equation, which is the range equation. So R equals R naught plus V naught delta t plus 1/2 a delta t squared. So we already know a lot of this already. So we know his end position is going to be 3.1 meters. His starting position, as we're going to make where he's at 0. So from that point of view, he's at 0. His initial velocity is 0, so you can cross this out and make it 0. His acceleration is just gravity, so 9.8, and then we have t squared. So now you can rearrange that, and that will give you square root of 2 times 3 times 10, or 3.10 over 9.8 equals t, and t will equal 0.80 seconds. Now that you have that, you can use this equation, and this is for part A, sorry. V equals V naught plus A average is the acceleration times delta t. So like we said before, we want to solve for his velocity when he hits the ground. His initial velocity is 0, acceleration is gravity, and we now have the time. So V equals 0 plus 9.8 times 0.80, which equals 7.79 meters per second. Sorry, I gotta hold this board up so it doesn't fall over. Alright, so for part B, it says if we treat the man as a particle, what is his acceleration, magnitude, and direction as he slows down if the acceleration is assumed to be constant? So that's kind of important, assuming that the acceleration is constant, because that's going to allow us to use this problem. So for part B, we're going to use Vy squared equals Vy naught squared plus 2 AY, the AY, times y minus y naught. Yeah, we're solving for this. Sorry, I wrote it differently in my paper. So we can rearrange this because we have a lot of the information already. We have the final velocity, we have the initial, and we have the change in y. So when you rearrange this, it gives you so you have your initial velocity over 2 times delta y equals equals acceleration in the y direction. So if we plug that in, we get negative 7.79 meter squared over 2 times 0.6. So now we can plug that in, and that will give us 50.6 meters per second squared, and since it's positive, we're going up with that. That's the force that's being applied or sorry, the acceleration as he slows down. Alright, and now part C. We gotta draw the free body diagram. So this one's a little tricky to solve. So we have his weight going down. We have normal force, which is opposing the weight, and then also we have the force of the ground acting on his feet. So we need to find the force for his feet. Let's see. What is the net force on him? Yeah. So the net force is going to be these two combined on him. So at his feet, we'll say F feet, he will feel the force of the ground and normal force acting on him. So it'll be the force of the ground plus the normal force. And we can find the force of the ground and the normal force because when he's landing, this is his acceleration going up. So that'll be the ground, and we just multiply that by his mass, which we were given as 75 kilograms. So you get, sorry, this is the sum. So the sum of the forces on his feet is the 75 kilograms times the 50.6 meters per second, because it's just you're just using this guy. F equals ma. So this force equals his mass times the acceleration of the ground on his feet plus his normal force, which is equal to his weight, which is 75 times 9.8. And you add those together and you get 4,530 newtons, and they want you to also give that in terms of multiples of his weight. So if you convert that, you will get 6.6 or 6.16 mass times acceleration, so mass times gravity. So just divide that by his mass and gravity.